So let's take 2D for example. Okay. So I have to try to draw something in 3D. So this is my x, y. What should this axis be? T, not z. It's a 2D. There is no z. And within this I have, my variables are like this. These are the coordinates around my E cell. So how many E cells have I drawn? 1 or 4? 4 E cells is what I have drawn. Okay. So yeah, there's only so much we can go from here. So let's look at the top view. Okay. So top view of this same thing, what does it look like? So I will draw this here. So there is a x, so this is spaced apart by how much? Delta y, and this is spaced apart by, what equation do we want to use? We can use the equation dH by dt is related to curl of E. Okay. So we are looking at again which polarization? We are looking at TE polarization. So TE polarization will have H Z EX EY. So these arrows refer to values of what? These unknowns are unknowns corresponding to what? EX and EY. And where is my HZ? It will at the middle over here. Okay, or I can also choose it over here, does not matter. Okay, so let's write down this equation. So mu naught, so dB by dt, right? That's the first thing. So that's mu naught H. So H n plus half minus H n minus half divided by delta t. That's my dB by dt. Okay, and that is going to be equal to curl of E, negative curl of E. So let's again write this down, Ex at n, I plus half j minus Ex n I minus half j. What should I divide this by? Delta y or delta x? Delta x. This is the first term, and the second term is, actually something is not right. This, yeah, exactly. So this is Ey. So Ey is, so this is the origin over here. So Ey is being evaluated at I plus, no, so this should be Ex only, and this should be delta y. Yeah. Yeah. So okay. Yeah. So we are changing only x coordinates over here. So this should be delta x over here, and then this should be Ey. And Ey is actually not being evaluated at, so if this is the origin over here 0 0, Ey is being evaluated at not at half integer in x but at integer in x, right. So this should be, and we have to rewrite this whole thing. Yeah, so this should be I comma j plus half, right? Is this right? And I comma j minus half. Does that look right? So, we are taking the difference between this guy and this guy. So, the I location is the same. I minus 1. Then this should be then this becomes delta y. This is right? Right. So, let's write, actually what we should do is write down the equation. So, we have mu naught del b by del t, sorry, del h by del t is equal to minus curl of E, okay, and we are only looking at the z component. So, this will become, what does this become? The first term will be del by del, there is a minus sign, right. So, del by del y of E x minus del by del x of E y. This is the expression that we want. Yeah. Yeah, so this is actually, so okay, the grid is let me use a different color. The grid is this. This is still the grid I am considering. Okay. Now are our expressions correct? So the first one is Ex partial derivative with respect to y. So then this expression that I have written is incorrect, right? This is x. Okay, let's start from scratch over here once again. This time we shall get it right. Okay. This is the first term we are looking at, Ex partial derivative with respect to y. Okay. So, this is Ex. What is the location? So, I am subtracting this and this, right. So, Ex I plus half right and j plus 1 minus Ex I plus half j. Okay. Now we are getting there. The next term is E. So, dey by dx, right. So, Ey. So, it is this minus this, right. So, this is going to be I plus 1 j plus half minus Ey I comma j plus half, right. We did not actually need to write it, but it is good practice for us to write it. Okay. Now, look at, let us get back to what we were trying to do, stability criteria, right. So, we have to find out the shortest distance that a wave could take. So, these in this top view diagram over here, these are sort of, we can imagine 4 nearest, I mean in one E cell, all these 4 values are involved in calculating h at a future time instant, right. So, this is my h at future time that I want, right. Everything else is past, h n minus half is past, these are all happening at what, n, right, correct. Of all of these things, which of the distances is the shortest? It is going to be this distance between these 4 points that I have, 4 arrows that I have drawn over here, 1, 2, 3 and 4, which is the shortest distance? It is this dashed green line, right. So, we are talking about a wave that is physically traveling, okay. Now, we want to do time, the philosophy is we want to do our time updates before the wave travels to the next to the nearest point, okay. So, the minimum tau, minimum time taken to travel, right, the best case can happen when the wave is traveling, for example, in this direction like this, then this is the shortest, because this is longer than, for example, this distance, right, because it is on a diagonal. So, how much is this distance equal to? So, delta x, delta y is the grid spacing, delta x by 2 whole squared plus delta y by 2 whole squared divided by speed of light. No, before I do a time update, yeah, it's going to travel, the wave is traveling from let us call this point A and let us call this point B. Before the wave travels from point A to point B, I should do my update, because my update equation has all of these points in it. So, before the wave travels from point A to point B is when I do my update, right. So, in other words, we can say that delta t should be less than this tau. Need not be. Who said that they are same? Okay. I mean, I can make a simplifying assumption that delta x equal to delta y. In that case, so assume that is the simplest case, delta x is equal to delta y is equal to, let us say, delta s. Okay. So, what does this tau turn out to be? Delta s squared by 4 multiplied by 2, right. So, this becomes delta s by square root 2 c, and for update equation to make sense, this delta t should be less than tau. So, it implies that delta t less than equal to delta s by square root 2 c. Okay. So, c delta t this is in 2D. So, an additional factor of square root 2 has come, right, just because these points are arrayed on a square and you are looking at the diagonal between the midpoints. So, can you guess in 3D what will happen? Exactly, I will get a root 3. I am just looking at the shortest distance. I want to do my update before the signal gets there in computation. So, which is harder? 1D, 2D, 3D, if you were to classify them in terms of computational resources. 3D is the hardest because delta t has to be even finer, right. Now, the bounds on delta t are getting tighter and tighter. Now, delta t in 1D could be delta s by c. Now, delta s by c is not good enough, delta s by root 3 in 3D, right. So, higher dimensions imply a finer time discretization. Right. So, what we have done, if we summarize what we have done so far, we have looked at the, I mean, we did the space update, we did the time update, then we looked at accuracy, under what condition, not accuracy, stability, under what conditions does a wave appear like a wave, and we found out what is called this Courant stability criteria. Okay. Now, next question we will ask that is it good enough? Okay. So, you can ignore the text written for now, let us just get to it step by step. So, stability I have got, but is my answer correct? That is the next question, that is meant by convergence. Okay. So, we will go through this very systematically. What do we start with? What was our absolute starting point for FDTD? Before E cell, Maxwell's equations, i.e. partial differential equations, So, we start with a PDE or a set of PDEs. Right. What did we do to this PDE? Next we went to E cell, right. In other words, we discretized it, right. So, we went, let us draw a long arrow over here, we discretized. Once I discretized, what kind of equations did I get? Were they linear? We used Taylor's theorem, we substituted a derivative by function values itself. So, I got a system of equations, right. So, I can write this as system of algebraic equations. Okay. So, what does so I've got this discretization which has given me system of algebraic equations. Another question that you can ask is this discretization depends on delta x and delta t, right. Obviously, that is the discretization. So, you can in fact go in the reverse direction and ask consistency, means this system of equations which I have discretized, is it consistent with the actual PDEs? That is one question you can ask, legitimate question. Then okay, let us leave that for now. Once I got a system of algebraic equations, what did I do? I solved them, and so solving them gave me an approximate solution. And under what conditions did I get this approximate solution? Stability, right. Under stability, the approximate solution that I got, I mean, made sense. So, there is a notion of stability in going from here to here. Okay. So, from these three sort of square boxes, is there something that is missing still? I have the PDEs, I have a system of equations, and I have an approximate solution. What other thing can you think of? I mean, the hint is that I have drawn three boxes, the actual solution, right, exact solution. So, we can call this the in the olden days where there was no computation, you tried to go from here to here by doing what? Analytical, right. But we know that is not possible many times, right. That is why you have numerical method. So, what is this? What should I write for this arrow? Convergence, right, that is what is convergence. Mathematically, how will I write convergence? Under what conditions? I mean, how will I have an approximate solution and I want it to converge. So, what is the notion? You can say delta x delta t tending to 0, that is when I will get that true solution. In real life, do I actually have a true solution to compare convergence with? No. So, then what is our notion of convergence then? Numerical convergence. Subsequent discretizations do not differ very much in their answer, right. Beyond a certain point, discretizing it even finer gives giving you basically the same answer to machine epsilon. So, that is our numerical convergence, right. So, stability we have seen, solution does not. Okay. So, now because convergence is hard to do, here is a theorem by Lax and Richmere which is very crucial in these things. So, what is it saying? So, it is given a properly posed linear initial value problem, okay, and a finite difference approximation to it. So, this is what is given to me, okay. So, this is given. What is it saying? It also should satisfy the consistency equations, okay, that is fine. Then it is saying that if you can give me stability, stability is necessary and sufficient for convergence. Okay. So, this is one of those theorems which mathematicians make, which in practice as engineers we do not tend to use very much, but you should know if someone asks you what is the guarantee that your solution will converge to the true solution. If you do not know the true solution, how will you answer that person? You can't. But this theorem can be quoted in reference saying that my solution is stable. For example, in FDTD what will you say? Look, my choice of delta t respects the Courant stability criteria, therefore it is stable. By this theorem, it is good enough for me to have a convergence in my solution. And what kind of convergence will you be able to show numerically? I mean, you will be able to show numerical convergence. So, then you have solved the PD. Otherwise, someone will say, okay, you have solved it, you have got some solution, but what is the proof that this is the true solution? Right. So, stability, the bottom line is stability is the important thing. Okay. So, when you look at commercial FDTD software, one of the most important knobs is this Courant stability factor. You have to make sure that it is obeying it such that your stability is satisfied, therefore convergence is also satisfied. Okay. Any further questions on this? Right. As I mentioned, in practice, this is apart from just making sure that the Courant factor is satisfied, there is not much practical use as an engineer that we will have for this